just a few more examples of being able to work with these trigonometric functions. So we have y equals sine x plus cos x over e to the x, and we're looking to find the derivative of that. So again, what we notice is that we're going to have to utilize a different rule because now we have a quotient of two functions. So we're going to have to use, not surprisingly, the quotient rule. And you might remember quotient rule says that we have our f over g quantity prime, and that's equal to f prime g minus fg prime divided by g squared. F is generally defined as the numerator, so let's just define f as sine x plus cos x, and let's define g as e to the x. F prime, easy enough to find, that's going to be cos x minus sine x, and g prime, even easier to find, is just going to be e to the x. And now we're just going to throw it into our formula to be able to find our dy dx. So dy dx, by using our formula, f prime g is going to be e to the x quantity cos x minus sine x minus fg prime, and I'm just putting the e to the x's in front to make it easier, more traditional. Usually we put a monomial term in front of a binomial or trinomial, etc. term. So this is going to be minus cos x minus sine x. I'm sorry, fg prime is going to be sine x plus cos x. So sorry about that copy error, but I caught it. So this will be sine x plus cos x. And finally, we're going to divide that by e to the x squared. Now we are going to simplify this, and there's a couple ways we can simplify this. So one thing you could do is you could factor the e to the x out from both of the terms in the numerator, which is what I'm going to do. So I'm going to rewrite this as e to the x, and inside I'm going to distribute the negative to these two terms. And so what we'll end up with is cos x minus sine x, and then we have a minus sine x minus cos x, and then we're going to divide all of that by e to the x squared. Okay, now another way to write e to the x squared, if you wanted to, would be e to the 2x, but I'm not going to write it like that to keep it intuitive as to what we're going to do after we go through and simplify. All right, so now let's simplify. Inside the brackets, notice factoring helped us a little bit because that canceled out the cos's. Notice that we have e to the x squared in the denominator. So really, e to the x squared can be thought of as e to the x times e to the x, which means we can cancel one of those e to the x's out by just discretely listing them. In the numerator, we can write this as minus sine, or minus 2 sine x. In the denominator, now we just have 1 e to the x. All right. Another way to write this, not that it's going to be any prettier, minus 2 sine x divided by e to the x. Either of these are pretty simplistic. And that's what we're looking for whenever we try to work with this quotient rule is, if at all possible, make sure you simplify when you can. So a very common problem that you're very likely to be tested on for examination is to be able to find the equation of a tangent line. Right? And we're going to be able to check it as well by utilizing our calculator. So let's find the equation of the tangent line at y equals 8x squared plus 5 sine x at the point 0, 0, which is our origin. All right, so first of all, we need to find the slope. So dy dx, which is really just y prime, which is f prime of x, whatever you want to think of it as. This one's really easy. That's going to be 16x. Now notice we're not using a product rule because there's a plus sign in between there. So we just use the general power rule, and then derivative of 5 sine is going to be 5 cos of x. And what we're going to do is we're going to substitute 0 in for x, because we know that this is where x equals 0. So now we're going to find f prime at 0, which is 16 times 0 plus 5 cos of 0. Right. And remember, 0 means 0 radians. All right, so on the unit circle, now of course we could use our calculator and cheat, But remember, this is the point on the unit circle 1, 0, and the cosine is the x coordinate. Right? So you might remember that on a unit circle, the trigonometric functions are defined as cos t comma sine t for some parameter t on the unit circle. So remember, cos is really the x value and sine is really the y value from trigonometry. So at 0 radians or 0 degrees, same thing, this is what we end up with. So we really end up with 5 times 1. And by using advanced multivariate numerical methods, 5 times 1 is 5. Now, is that the equation of the line? No. That is just the slope. Remember, the derivative finds us our slope. So this is our m for our problem. So now we have to go back and we have to remember our formula for the equation of the tangent line. Y minus y1 is mx minus x1. What is x1, y1? X1, y1 is our original point, 0, 0. So we're going to substitute y minus 0 is equal to 5x minus 0. Clearly, the zeros mean absolutely nothing to us in the problem. And so our equation of our tangent line is y equals 5x at the origin. How do we check this? We go into our calculator. And we should check to verify that the function does indeed have a tangent at the origin of 5x. So let's graph it. And our original function, and we have two functions in here, probably from the last time we checked this. Remember our original function was 8x squared, and then we had plus 5 sine of x. And then our tangent line is just 5x. Let's see if this makes any sense whatsoever. Now, of course, before we graph this, one thing that we have to make sure of is the mode. For those of you guys that may have forgotten, you don't want to be in degree mode. Right? So let's see what happens if we put in degree mode, just for fun, because I have a sick idea of fun. And I'm going to graph this. All right, and we get something like this. I don't know if that looks tangent, but it might be. However, let's go ahead and switch the mode back over to radian. It might actually get us something different this time. So let's make sure that's in radians. Yep. So y equals, and we're going to graph. Ah, that's a lot better. Let's zoom in just in the origin. And one way to make sure we're right, zoom in, is to make sure, if we zoom in, that the line and the curve should be basically melding into one. I'm not sure what's going on here with this. So let's graph it. We're going to zoom, and we're going to zoom in. I think I hit Z box instead of zoom in. So let's try zoom in. There it is. And we could zoom in again if we really wanted to, just to verify. There we go. And the line and the curve look almost the same, right? If that's not the case, to where they're not laying on top of one another almost, then at that point you don't have a tangent. You can more likely have a secant line, or they're not even intersecting. All right, so I strongly urge you, once you get your equation of your tangent line, plot the original function as well as plot the tangent line on the same graph to verify that they are indeed coexisting with one another and they support one another. Right. So in the next section, we're going to move away from just trigonometric functions, and we're going to start one of the final rules of differentiation, which is unfortunately one of the most complicated rules, because now we start taking the derivatives of composite functions.